let me summarize a little bit here because I'm going to return to this inverse computation. We start with the linear equation, and we're interested in computing the inverse. That's basically what we do when you solve an equation that has one solution. So when we looked at this computing the inverse of a 3x3 case, for example, it's actually bits and pieces of the following equation. This is a coefficient matrix. We want to figure out inverse of this 3x3 matrix. So if you multiply that inverse matrix, it becomes 1, 0, 0, and 0, 1, 0, and 0, 0, 1, namely the identity matrix. So if you focus on one column at a time, and that's going to be a solving linear system of linear equations. So next thing we did is that we kind of treat this equation as a two-variable y and z, and kind of treat the x as a constant. So we focused on that 2x2, and to solve for y and z that are in terms of x, and we went back and substituted back and realized that x and y and z is written in this form, where the common denominator is neatly written like this: a1, a2, a3, the top rows, and there's a 2x2 matrix bits and pieces shown up here, and then sign flip. From this definition on, the determinant has this nice property about the multilinearity and skew symmetric property, and we went through the proof that proof for this determinant as a function on column vectors, and that doesn't hold for, if you think about it, if you try yourself, it's a bit tricky to apply to rows, but we have, using this multilinearity and skew symmetric property, we introduce this version of the determinant as a sum of the product of a permutation with the sign of a permutation thing. From there, we proved the determinant is equal to the determinant of its transpose. So that'll allow you to look at the function as map on the rows, and all the linearity and skew symmetric property transferred over to that. So that's what we have done so far. So now what I want to do next is kind of finish off this problem. We looked at only 1, 0, 0, and there's this d showed up and it was a common. What about second column of this identity matrix, 0, 1, 0? Okay, so in that case, we're going to look at the 0 row and then 0 row. When you look at it here, the solution sets are linear. The structure of the solutions is linear because of the 0 and 0. That's why there's nice cancellation and solutions are nice. So that's the motivation we're isolating these two things here. So this one, we can isolate A2 and C2. So we look at this equation as x for x and z here, treating y as a constant. Then we're going to be dealing with this. So let's solve this xz equation for x using the Cramer's rule. We have to use this determinant. Let's think about how we label this determinant. For example, we're looking at a1, a3, and c1, c3. Before, with this b1, b3, and c1, c3, we label it d2 because it misses all the second column entries. Now we're actually dealing with the first and the third row and this various column, so we're going to label it like d2. It's consistent with the d2, and here we're going to label it e2. This e2 is missing the second row, but only dealing with the entries in the first row and then third row. That's what you see here. So it's going to be e2, determinant of that. And this one, x is a first variable, so the first column is replaced by the right hand side. So if you factor out y, that's going to be e2 down there, and a2, a3, and c2, c3. a2, a3, and c2, c3, that'll be labeled as e1 because it misses this first column. So e1's here, e2's there, and negative y is factored out. Now if you do the same thing for the z, the Cramer's rule again, with the coefficient matrix, determinant e2 goes down there, and z is the second variable for this 2x2. So this negative a2y, negative c2y goes to the second slot, second column, and y factors out. If you look at a1 and a2 and c1 and c2, that's the correct order. So we have negative factor, negative y factored out. And that one, a1, a2, c1, c2 must be E3 because it means this third column. So there it is. With this one, we go back to this equation we didn't play with, the second row, and plug in this into that equation and solve for y. So I'm going to write it up there. So we have, if you look at the second row, that is b1x, b2y, b3z set equal to 1. Now we found x and z like this in terms of y because we chose these 0 rows. That's why it's nice cancellations there. So negative y, and all these things replaced up here. Now all the y's are common. And I'm down here and I've factored out. And e2 is a common denominator. I've factored out. And we're left with this b1, e1 minus b2, e2 plus b3, e3. And then negative y is factored out. Okay, so y will be this long thing, and in the denominator, and e2 in the numerator. That's what y is. But let's look at this determinant, b1, b2, b3. That looks like a determinant. That's the whole point. Down there, it looked just like the way we defined the determinant in the earlier stage. So if I arrange it like this, b1, b2, b3 up there, and think about where this e1, e2, e3 come from. E1, E2, E3 are the 2 by 2 matrices from the first and the third row. So if I put the first and the third row here in the second and the third row, the determinant of this one, according to our definition, this determinant of this one is exactly appearing in the denominator. Okay? So that whole thing is going to be down there, but it has negative. And if you compare this one with the determinant of the earlier one, which we call the D, is that we just swap this first and second row, right? Our result is for both the rows and the columns because of our result on the determinant of A is equal to the determinant of transpose of A. So these two things, as you swap this first and the second row, is going to change the sign of the original determinant. So once you arrange it like this, you recognize this one as a negative. This whole thing is negative d, but they have already negative there, so the entire thing is going to be just simply d. So I wrote that that part here with the negative d, and then we're rewriting that x and z in there with the negative e2. Wait a second, did I do this wrong? Yes, I did it right. I was just a bit confused by negative here. Negative disappeared down there. That's what we're talking about, so it's right. So we get this x equals this previous formula where y over e2, I forgot to record it here, y over e2 is the determinant d, so that replaces d down there and d down there, and y is recorded here, e2 over d, right? So e2 over d, e2 over y over e2 was going to be 1 over d. Sorry about all this confusion. You have to start from here, y equals e2 over d, and then if you use it here, then you get this result. Again, the point is that all the x and y and z is neatly organized like this, and the d, the same discriminant, and in the denominator, and e1 and e2 and e3 kind of had the same pattern. You can see the sign's a bit different, but that comes from the skew symmetric property. But this is the answer. So we're not going to go through for the z part, but we're just simply going to kind of sketch the outline. If you put, instead of 0, 1, 0, 0, 0, 0, 0, 1, that's the last column of the identity matrix, then we're going to play with these first two rows and just play with x and y, treating z as a constant. You go through exactly the same method. What you're going to end up at is that z is going to be f3. That would be the determinant of these 2 by 2, a1, a2, and b1, b2. The 2 by 2 matrix formed by this first and second row, isolating one of the columns, and removing the one of the columns. Now let's focus on the denominators, c1, f1, and negative c2, f2, plus c3, f3. Again, this looks just like the way we defined the determinant for the first time. So I would put this c1 and c2 and c3 up there, and think about what this f2 and f1, f2, f3 look like. They came from first and a second row. So if you put the first and the second row nicely like this, that'll exactly pick up the denominator. The determinant of this one right here is what you see in the denominator there. So let's compare this one with our original coefficient matrix. Is that A and B are kind of keeping the same order in terms of how it's written. So if I move this first row, C rows, all the way down to the bottom, and then we're going back to that takes 2 swapping, so it's even number of swaps. So therefore determinant value remains the same. So therefore this is actually equal to D. So going back and substituting all that, X and Y and Z are organized in this way this time. Alright, so this time to put everything together is the following. This is a coefficient matrix, and we found that X and Y and Z we were looking for at the beginning. That gives you 1, 0, 0. Okay, so if we can forget about the second 2 columns, think about X and Y and Z we're trying to solve. With this matrix equation, that gives you 1, 0, 0. That's the very first one we tried. From there we define the determinant and so on. So that has a common denominator D, and X, Y, Z's column vectors. You should write it like this vertical. Second one had the same common denominator D and E1, E2, E3, but that has a weird sign, different convention. And the third one picked up the correct sign again, but they all look like this. And all these D and E and F are the 2x2 matrices that come in out of this. So that is the formula for the inverse of a 3x3 matrix, if entries of 3x3 matrix like this. So I wrote it up here. Okay, so now this might be the pretend version of how you discover the formula of the determinant and how you prove all these properties that's introduced in the book. So it's a very motivational approach to the determinant, but the following is usually how mathematicians present the result. It's more straightforward result. You just show that this matrix we found here, it simply just is the inverse by just multiplying it. So that will be a more straightforward proof. So we're going to go through the more straightforward proof. It's a lot easier than the motivational approach we did over there. So here's what we're going to do. All we have to show now is verify that this matrix times that in this order is going to be the identity matrix. So first I ignore this 1 over D, just looked at this D1, D2, D3 with a negative in there. I'm going to multiply this column to this row. That's how you do the matrix multiplication, right? We multiply this column to this row. So if you do that, we have A1, D1 minus A2, D2 plus A3, D3. Okay? So that is exactly the dot product. Okay, so I'm not remembering why I did this one in the dot product right now, but this will be sufficient. Maybe it'll come back. So this is exactly the way we define the determinant. So I'm going to call that as a determinant of M, if that's called M. So there's this dot, and the product of these two vectors, dot product, it's realized the determinant of M. Rather than doing this or multiplying this in the second row, I'm going to actually focus on second column multiply to the second row. We'll do all this combination, but here it is. If you multiply these column to the second row, then this is what you get. Now this is B1, B2, B3 multiplied to determinant of 2x2 matrix out of this first and the second row. So if you swap these two rows, you get exactly this. And by doing that, determinant only changes the sign. So if you put the negative out there, it's going to be the same determinant of M. So let's look at the third one, which is the following. This third column multiplied to the third row, then again it looks like a determinant definition. So if you have the C1, put it up there, that is exactly this determinant of this is exactly the determinant of that 3x3 matrix, but it can be done by swapping 2 times up there. So sign doesn't change, so determinant of matrix with a C1, C2, C3 in the top is actually exactly equal to the determinant of this exact one. So all of them actually happen to be the common number. So those make the diagonal terms with a common term determinant M, determinant of M, determinant of M. So what we have calculated here, if you take this product, then what's going to happen to the diagonal part is they're all common scalar, common number, determinant of m. And that's so let's look at other terms. For example, if I multiply that first column to the second row and then third row, for example, if you do the second row there, we have this determinant looking properties. Alright, D1, D2, and D3 is exactly the 2 by 2 matrix coming out of this second and third row, right? But B1, B2, B3 showed up, so if you put B1, B2, B3 instead of A1, A2, A3, that will be this will be the determinant of that matrix with the B1, B2, B3 in the top row. As soon as you do that, you know this B1, B2, the first and the second row is repeated. For that, you know it's a determinant of 0. Okay, so this is using that multilinear and symmetric properties. That was and the permutation definition and transpose doesn't change determinant. All that plays in to explain why this one multiplied becomes this identity matrix. So that's 0. If you do the third one, if you multiply that first column to the third row there, then you get this one. Okay, but that's exactly the determinant of this matrix as I written there, C1, C2, C3, and this second and third row is exactly the same as the original matrix. Then again, the first and the third row is the same, therefore it's going to be determinant 0, so that must be equal to 0. That's neat. Now let's look at the second column again. The second column is multiplied the first row and the third row. We already did the second row. So if you do that to the first row, this is what you see, A1, E1, A2, E2, and A3, E3. But there's a negative out there, so I forgot negative, positive, negative. Okay? But that's without the negative, if you flip the sign, and that looks just like this one just looked like a determinant of this matrix right here. A1, A2, A3 in the top. E1 actually, yes, and E1, E2, E3 uses this first row and third row. So if I put the first row and the third row here in the second row and third row in this matrix like this, the determinant of this matrix is exactly that. Okay? But you know this one is 0 because first and the second row is the same. So that makes this one 0. The difference between this one and the product, dot product of the second column here and the first row is just a sign. So if this is 0, that product must be 0 as well. So let's look at the third one. If the second column is multiplied to the third row, and you get exactly like this, not sign change or anything, exactly like this, right? So we'll put this C1, C2, C3 in the top row. What happened here? So I think I made a mistake. C1, C2, C3 is supposed to go in the top, and E1, E2, E3 has to be down here, A1, A2, A3 there. But it changed the sign as we swapped these two, but it turned out it's a 0 because it's rows repeated. So that also makes this 0. Sorry about the mistake. The C1, C2, C3 goes to the top row, and A1, A2, A3 is supposed to go to the second row. All right? So I tried this first and second row column so that they're slightly different ordering, but from there I think you can do the third column, so I'm going to skip the third column part. So here's a conclusion. If you're looking at this 3 by 3 matrix, its inverse matrix is 1 over the determinant of this matrix. You can use this first row and then determinant of 2 by 2 here and that combination. And this matrix part's interesting, that D1, D2, D3 made out of the second and third row. E1, E2, E3 is made out of first and the third row. F1, F2, F3 is made out of first and the second row. All 2 by 2 matrices. But the way it's written is not row way, it's a column way it's written. Because the way the matrices multiply to each other is the dot product, it goes, the column is multiplied to the row. So that's one way to remember why this one has odd orientation of this, why the D1, D2, D3 is going down like this, not going across like that. Also, the sign convention, you're computing all the determinant, but as you go to the right, it always flips the sign. As you go down, every cases the sign flips. This phenomenon can be, carefully proved, but I think if you think about the skew symmetric property and how we're swapping these rows and the relative locations, I think it's kind of easy to believe that. So we're basically done with this, my attempt to give a motivation to the definition of the determinant and then its important property, linearity and multilinearity and skew symmetric property, and then inverse formula and so on. But this Kramer's rule is really summarize everything nicely, and see how this one works really is a good recap of everything that we have discussed. So I couldn't resist the temptation to put this Kramer's rule at the end here. So bear with me. I know it's been a long video, but bear with me with this last bit. This is kind of cool. So Kramer's rule goes to this very fundamental question we had. We have 3x3 matrix, and there is this system of 3 linear equation. Put it into a matrix form. X, Y, Z are unknowns, and all these A and B and C's and S and T and U are given. The goal is computing this X and Y, Z. Can we write down X, Y, Z in terms of these things? What is the algebraic formula? Now we have this powerful tool, the inverse matrix. So all you have to do is multiply to the left-hand side, this inverse of this coefficient matrix. Then they cancel. The left-hand side just simply becomes this X, Y, Z. Right-hand side, by the way, has this column vector STY from the left, and this inverse matrix is multiplied. What was the inverse? Was this 1 over the determinant of all this entry made out of that 2x2 matrices, determinant of 2x2 matrices there. Okay? So I wrote it up here, and then what we're going to do, we're going to strip off x equals the first row, y equals the second row. As simple as that. So here it is. X is going to be one of the determinant of the first row multiplied by this column STU. So STU goes there. Y will be the second row multiplied by this column. STU goes to DEF and so on. And Z will be third row multiplied by this column. STU again, and with this DEF. And with the third entry, I circled these entries because that's important to focus on. Okay? Now to look at this matrix, and let's think about what these DEF is. Right, D uses the second row and the third row. E uses the first row and the third row. F uses the first row and the second row right there. One means that we're looking at D as your second row and the third row, and one means that you remove that first column, then you have this nice 2x2. That's the matrix. Okay, so remember that the D1 is this corner block. E1 is going to be first row and then third row, and removes the first column, so it's going to use A2, A3, C2, C3. They're all in here, that's the point. F1 uses the first and third row, and it also removes the first column, so if you remove it, we're left with A2, A3, B2, B3. Good. So all of these D1, E1, F1 are exactly playing with this right sides, this part of this matrix, and we're multiplying STU in there. So if I put STU in place of A1 and B1 and C1, and then if you transpose, and you can see that's exactly the determinant of, so we realize this one here is a determinant of something. So let me show you. So the answer is this. Determinant of M is copied. If I put STU there, and then I keep all these columns, second and third columns, and then you take that and transpose it and compute the determinant of this one, and you will see that exactly shows up like this. All right? So you can do that definition not along the row, you can do along this column, because the transpose doesn't change the matrix, determinant of the matrix. So let's do this part here. Again, D2 will use the second row and third row, because it's 2. We remove this B2 and C2. We have this B1, B3, and C1, C3. Okay, so if you look at this one, that uses also first row and the third row, it removes also the second column. So we're always dealing with this first column and third column. And all these 2's in a circle removes the second column exactly. So if I replace this one with STU, like this, STU, and it's kind of close to that, but we want to have STU on this side, just like we did before, just so that we can do that in a transpose and applying that 3x3 determinant definition. So we first flip it, then this one will come out, but difference between this one and this one before you flip it is going to be sign difference because it involves one flip. So that's why you don't do ST, negative T and U, but do negative S and T and negative U, so that these two things are equal to each other. Okay? So the third one, because it's all using the third, first and the second column, and remove this third column here, everything and has to be on here, then the third column will be replaced with STU, like that. So to realize this one is determinant, we can put this STU in the first row and then transpose. Then if you apply the definition of our 3x3 determinant, you will see exactly this one. And then difference between this one and that, it involves 2 swaps. The sign doesn't change, so this is exactly equal to that. So x and y and z is now organized like this. This 1 over determinant of m, and this is exactly the coefficient matrix, except the first column is replaced by the right-hand side vector. And it's y is the second entry of the unknown vector. Second column is replaced. C is the third column, third entry of the unknown vector. Third column is replaced. So this is called the Cramer's formula. From that, all determinant algebra is kind of, at this point, if you have keeping up with the material, I think it's fairly easy to see. And another advantage is that from this point of view, it's fairly easy to see how this one generalized from 4 and 5 size matrices, square matrices. So at the end, finally, let me show you this a definition of a 4x4 determinant of 4x4 matrix, and it uses the first row, and then from the skew symmetric property and multilinear property that I think we have already used, that it doesn't matter which row you use. You can flip it and then can do determinant calculation if you keep track of the number of flip correctly. So that was the definition, and I hope you understood why it's defined like that. Another thing was this permutation definition. So if you use that algebraic property, you can unfold everything down to this shape here, where you see all the terms in the product and organize it in this way using n factorial permutation, number of permutation, and for each of the term has this plus and minus attached to it, which is determined by reordering this first entry of the indices of each term. All right, thank you very much. Thanks for your patience. It was a long video.